Hi, this lecture is about machine learning methods in econometrics, and this video is going to be a little different from what we have done so far. What we have done so far is that we have been looking at machine learning methods from the eyes of you could say, a machine learner. That is to say that this course has not been that different from, say, other courses that you could have followed at other parts of our university. For example, the Department of Computer Sciences at the Sciences Department. However, today we're going to do it a little different, and we're going to look much more at machine learning methods from the eyes of an econometrician. In particular, what we're going to do today is that we're going to ask ourselves the question, well, how could machine learning methods help us in econometrics, in causal econometrics? And for that we are going to look at two different methods that have been developed in the last couple of decades, and that is first of all the so-called post-double selection estimator, and apart from that we are also going to look at the so-called synthetic control groups. But we should take into account that even though some of the publications that we're going to look at are already more than 10 years old, at the same time we should realize that this is research that is still under development. Let me first of all look at the post-double selection estimator. Well, for that I first of all have to recap you a little bit with respect to some of the things that we have already dealt with during this lecture series, and probably also have already seen that in other courses. First of all, we have to look at the so-called causal outcome model. And we do already know that a causal outcome model essentially has two different observed variables. That is, first of all, yi, and second of all, we also have di. And if we first of all look at yi, which is usually called the outcome variable, yi can take two outcomes. Either it's equal to yi1 in the case that di is equal to 1, or it's equal to yi0 in the case that di is equal to 0. So apart from yi, we also have di, and di equal to 1 means treatment. That implies that, well, di usually also is called the so-called treatment indicator. Well, we do already know that the fact that we do only observe yi and di is going to give us problems. That is to say that, well, we would like to investigate the values of yi1 and yi0, but we only observe one of them. Well, we have already talked about these problems, so I would not like to talk about that too much right now. But we do also know already that under the assumption of unconfoundedness, that is the situation in which we are going to assume that there is no correlation between di on the one hand and yi0 and yi1 on the other hand, that means of course that the mean of yi0 conditional on di as well as the mean of yi1 conditional on di is equal to 0. If we're going to make that particular assumption, then we do already know that then the average treatment effect is of course generally equal to the mean difference in outcomes between y1 and y0. We do then know that the average treatment effect in that particular situation is equal to the mean of yi conditional on di equal to 1 minus the mean of yi conditional on di equal to 0. That's a thing that we do actually already know. And that is of course quite nice because of the fact that that means that under these conditions the average treatment effect is identified. That means it can be estimated. And there are, well, you could say different ways in which we can estimate it. One way to do that is to write it as a regression equation. You can write this model as a regression equation where we have at the left hand side yi, and the right hand side we have alpha plus di times beta plus ui. Well, and then we should realize that we can then show that under unconfoundedness the beta coefficient is exactly equal to the average treatment effect. In addition to that, we should also realize that under the unconfoundedness we also know that ui and di should be uncorrelated with each other. That's not that difficult to prove. But that means of course that estimating this model with respect to ordinary squares will give us then consistent and unbiased estimators of our beta coefficient and hence of our average treatment effect. So that's actually a quite nice thing, that in this particular situation there is no problem whatsoever. We simply are going to be able to consistently and unbiasedly estimate our average treatment effect. However, the main problem that we have is that unconfoundedness is almost never true in social sciences unless we use a so-called random control trial. You already know that random control trials are not that popular in social sciences, not because of the fact that, well, essentially they don't work, but because of the fact that they are, well, you could say, practical problems. That is a thing that I already discussed before. But the problem at the moment that we're going to have, that why actually do we not have unconfoundedness? Well, that is generally true as the populations of the treatment and the control group are different in terms of what you could say observed characteristics. At the moment that the observed characteristics are quite different from each other, well then at that moment in time we cannot expect that we can then simply compare the outcomes of the treatment group and the control group with each other. That is then at that moment in time impossible. In order to give you a particular kind of example, at the moment that we again are going to look at a medical treatment, then at that moment in time it could be possible that the people that are going to receive the medical treatment are going to be quite different in terms of, for example, symptoms that they have. That is probably the reason why they actually get the medical treatment, why, for example, a medical doctor decided to give these people a medical treatment in the first place, simply because of the fact that they are going to have particular kind of symptoms. And that implies, of course, that we're not only going to compare individuals that have differences in terms of their medical treatment, but also differences in terms of their symptoms. And that implies, of course, that the people that we are going to compare, they're not just comparable with each other. And that's, of course, a problem. And that is the reason why we actually are going to be not able to make the assumption of unconfoundedness, simply because of the fact that the people that we are going to compare, they are going to be different in terms of observed characteristics. As an intermezzo, we should realize that these individuals are not only different in terms of observed characteristics, they could also be different in terms of unobserved characteristics. Well, I'm not going to focus too much on that at this particular moment in time. And the reason behind that is that at the moment that we're going to also focus on unobserved characteristics, then things become much more difficult, and, well, that I'm not going to discuss over here. But at the moment that we're going to look at observed characteristics, let us now assume that we have a set of Zi, that we have a set of characteristics, observed characteristics, that we can denote by a vector Zi. So let Zi be the observed set of characteristics of a particular individual I. In addition to that, I'm also going to suppose that we can divide these characteristics in two unknown disjoint subsets, Z1I and Z2I. Now, of course, the question arises, what is then the difference between these two? Well, roughly speaking, I'm going to make that much more clear shortly. But roughly speaking, what we can say is that, well, in many situations, what we do have is a very large data set. We know a lot of things about a particular individual. Also, at the moment that we're going to look at patients that are going to get a medical treatment, then we might know a lot of things about a particular individual. For example, the symptoms that these individuals have. But we sometimes also have a lot of information of all the kind of diseases that these individuals had in the past. Well, you should realize that some of the information that we have might be very relevant, and some of the information might not be that relevant for our analysis. So therefore, what we're going to state roughly is that the Z1s that we are going to have are the, say, relevant characteristics that we have in our, say, data set, whereas Z2 are the, you could say, irrelevant characteristics that we have in our data set. But the problem that we have is that we actually do not know which of the, well, which, say, characteristics are relevant and which of them are not relevant. Now we're going to introduce what we call conditional unconfoundedness. What is conditional unconfoundedness? Well, conditional unconfoundedness means that well, the mean of y0 as well as the mean of y1 well, conditional on di and z1I, they should be equal to 0. What does this mean? Well, this essentially means that we have seen at the previous slide that unconfoundedness generally is of course not true. That is to say that if you're going to simply look at the treatment that individuals are going to have, then treatment usually is correlated with the particular outcomes that we have, y0 and y1. We do already know that at the moment that somebody is going to get a medical treatment, that the people that receive the medical treatment might be quite different from the individuals that do not receive the medical treatment. But now suppose that what we're going to do is that we're also going to take into account, say, the values of z. Well, then essentially conditional unconfoundedness means that if we also condition on z, well then y and d, they become again uncorrelated with each other. It's important to think about, I would say, particular examples. What we could do is that we could look at the examples, medical examples for example, in which actually unconfoundedness might be correct. At the moment that we are going to compare individuals with different kinds of, I would say, symptoms, then of course, well, we do know that D and Y, they may be correlated to each other. However, at the moment that we're going to look at individuals that have exactly the same kind of symptoms, well, then we could actually assume that the individuals are going to be, well, in terms of their treatment, if we're going to compare individuals that have exactly the same symptoms, and at the moment that we're going to then look at whether they receive treatment or not, well, then it might be a, well, proper assumption to assume that essentially their potential outcomes are going to be uncorrelated with their treatment. In words, conditional unconfoundedness means that for individuals with the same level of Z1I, the potential outcomes y0 and y1 are going to be uncorrelated with the treatment choice. And even though we can say that, well, of course, unconfoundedness is a very strong assumption, we should realize that conditional unconfoundedness might not be such a strong assumption. At the moment that we're going to make the assumption of conditional unconfoundedness, then we can look at the following regression equation. We still have yi at the left hand side, and now we have at the right hand side, first of all, alpha plus beta times di plus, and that is important right now, we get an additional, say, function gz1i plus ui. Ui we already knew about, and well, due to the unconfoundedness assumption or the conditional unconfoundedness assumption that we have made so far, we can expect that ui is going to be uncorrelated with both di and z1i. So that means that the mean of ui conditional on di and z1i is going to be equal to 0. In addition to that, we do of course now have this additional, say, function g. And g is now going to be a so-called unknown function of the realizations of our z1i that we have. Now we have looked at this so far, and now we do have a regression equation. But we should take into account that twice I have already talked about something which is unknown. The first thing which is unknown was on the previous slide, and that is to say that even though zi was known, we do know which variables that we have in our full data set. We do not know which variables actually belong to z1i and which variables belong to z2i. In words, it means that we do actually not know which, say, variables are going to be important for our analysis, are going to be relevant for our analysis in order to get conditional unconfoundedness, and we do not know which variables actually are not that important, that actually belong to our z2i. In addition to that, we also do not know what our function g is. We have of course written it theoretically, but we do not know what actually the, say, parametric form of g is. We should take into account that that is of course problematic. But let us first of all ask ourselves the question, what would have happened if we actually would have known both g as well as z1i? Well, then the world will be very simple because of the fact that then at that moment in time we could just do regression analysis. Depending of course on whether g is going to be linear or not, what we could do is that in the case that the function g is going to be linear, then we can simply do of course an ordinary squares regression, and then we can still show that the beta coefficient that we're going to get is going to be a consistent and unbiased estimator of our average treatment effect. However, at the moment that g is going to be non-linear, then we cannot do ordinary squares of course, but then we can still do non-linear least squares. And then at that moment in time we still can get a consistent estimator of our beta coefficient. That implies we are still going to be able to get a consistent estimator of our average treatment effect. So we should realize that at the moment that both g and z1i are known, then we are not going to be in any kind of problem. However, what we should realize is that that is not very realistic. It's more realistic to assume that we actually do not know g and z1i. Then the question arises, what are we going to do in that particular case? Well, let me first of all look at what we will do actually in standard econometrics. And that's probably what you already have seen a couple of times before during, well, your bachelor in econometrics. What we typically do in standard econometrics is that even though we do not, of course, know in reality the, say, function g, as well as we do not have any idea about z1i, we're simply going to make assumptions about it. One assumption that we could make is that, for example, g is simply going to be linear. That makes, of course, life a lot easier in order to estimate. In addition to that, what we're typically going to do at the moment that we're going to look at our data set, then we have many variables, of course, sometimes a couple of hundreds of them. And then what we typically do is that we're only going to select a couple of different variables that we are going to select essentially in our z1i in our model. And these are, say, the kind of variables that we expect are going to have some impact, of course, on our, say, outcome variable on yi. That's essentially what we typically do in econometrics. But take into account that there is a downside with respect to that. And that is that at the moment that we are going to make the wrong assumptions, for example, in the case that g is not going to be linear, or at the moment that we're going to leave out some of the z1i's that should actually be included in z1i, so we are not going to include all the variables that are essentially relevant for our analysis, that are going to be correlated with both yi and di, or maybe on both of them, well then what we should realize is that at that moment in time we're going to get inconsistent estimators of our average treatment effect. And it could even be the other way around as well, of course. We should even realize that at the moment that we're going to include too much into our z1i, then at that moment in time we're not going to only get inconsistent estimators, but we even are going to get inefficient estimators. Now the question that arises is how we're going to solve this problem. Or maybe better to say, well, how can we actually solve the problem that we have in standard econometrics? Maybe even better to say, how could machine learning help us in order to make our econometric methods better? Well, recap that we essentially have now two problems. We first of all have no idea about the function g that we have over here in this regression equation. But the other problem that we have is that we also have no idea about z1i, which z1i's should actually be included. Well, in order to solve this problem, what we're going to do is that we're essentially going to, well, split it up. We are first of all going to ask ourselves the question what to do with respect to the fact that the function g is unknown. So we first of all are going to ask ourselves the question what to do with respect to the function g when it's unknown, but with z1i to be known. And then after that we're going to ask ourselves the question what are we going to do at the moment that z1i is unknown as well. Well, in order to solve the problem of the unknown g, one can use a very flexible specification of z1i. What does that mean? Well, that means that apart from the fact that we're going to include z1i itself in a linear form, we could also include higher order terms. We could include z1i squared, or z1i to the power 3, or z1i to the power 4. We could even go to z1i to the power 10 or 20 or something like that. In addition to that, we could also include interaction terms. We can interact, for example, the first element that we have in z1i with the second element of z1i, or the third element of z1i, or the fourth, etc. We can relate that to all the elements that we have. Apart from that, we can of course also look at all the other, say, interaction terms. Well, that implies that we become very, very flexible. But note also that there is a problem here because of the fact that there's a trade-off. That is to say that the more terms that you're going to introduce, so the more higher order moments that we're going to introduce, as well as the more interaction terms that we're going to introduce, the more flexible that we become, of course, but we should also realize that we then have to estimate more coefficients. And the problem that we have, and that you already know with respect to standard econometrics, but I also have been talking about that during this lecture series, is that the more coefficients that we're going to estimate, the higher is also going to be the variance. So we should realize that there is already a trade-off over here. But generally speaking, what we can say is that we can now rewrite our original regression model that we had at this slide. We can rewrite this a little bit into another model. That is to say that we still have yi at the left-hand side, and now at the right-hand side we're going to have alpha plus di times beta. Well, that's essentially what we already had, but what we have to do is that we have to rewrite the function g. And we are going to rewrite it in this format that we have over here. We're going to introduce a polynomial because of the fact that what we have done so far, our flexible specification, was nothing else as a polynomial of z1i, and I'm going to denote that polynomial by p star. That means that what we're going to get is the polynomial p star, the different elements in our polynomial, and they're going to be multiplied by a coefficient factor gamma that we have over here. Well, what we should realize is that even though this polynomial is going to be very flexible, this polynomial will never be exactly equal to the original function d that we had. So therefore we have to introduce an additional term. That is going to be our approximation error. We're going to have an additional approximation error that is going to be added to the regression equation that we have, and we are going to denote that by R1I. Now we have to make a very important assumption, and that is that this approximation error is going to be uncorrelated to both di and z1i. In words, this means that essentially that even though of course the p star z1i could be different from g, it should still have all, I would say, systematic variation that we have with respect to z1i that's going to have an impact on yi. So only the unsystematic part could actually be captured by R1i. Well, if that is going to be true, then generally R1i is going to be uncorrelated with both z1i and di. Still we have our error term, our ui as well. But we should realize that in this particular setup, since both R1i and ui, they are uncorrelated with both di and z1i, we could in principle estimate this with ordinary squares. However, we should realize that we still have another problem. And the other problem that we still have is that we should realize that also z1i is unknown. But now remember that z1i was actually a subset of zi. Zi was the, say, whole set of variables that we had in our data set, a very large set of variables. And z1i was only a subset of that, of the relevant variables. Now what we could of course do is say like, well, but we could become even more flexible by essentially not including, of course, only the z1i's, which are unknown of course, but we could also include just all the zi's, then we know for sure that also the z1i's are going to be included. That means that we're going to get even another kind of model. That means that we still are going to have yi at the left hand side, but the right hand side now we're going to have alpha plus di times beta. That's still what we had from, of course, the previous slide as well. But now we're going to have a polynomial in zi and not in z1i as we had at the previous slide. And we should realize that, of course, that one is going to be different from the, say, polynomial that we had at the previous slide, because of the fact that it depends on more, say, variables. So therefore, instead of writing this as p star, I'm going to write it now just as p itself. So now we have a polynomial of zi. And still we are going to have the gamma, plus of course our residual term, r1i plus ui. And the idea is still the same. But we should realize that as long as, of course, r1i is going to be uncorrelated with di and pzi, then in principle this can be estimated by ordinary squares, getting, in fact, in principle, consistent estimators of our beta. But the problem that we are going to have is, as I already said, zi is usually large. If we're going to look at a medical example, then typically we do not only have information about, say, for example, the symptoms that a particular individual has at a particular moment in time, but we have much more information about the individual. For example, we have general health information, what kind of diseases had this person in the past. And then, especially if we have, say, a person that is not that young, that could contain, of course, a lot of information. In addition to that, we could even have additional, say, characteristics of the individual. What is the age of the individual? Whether the individual smokes or not? Whether the individual is married or not? Where the individual lives? What is the education level of a particular individual, etc. These are all kinds of things that might be relevant, but of course they also might not be relevant. And typically what we are going to have is that we are going to have, zi, the size of zi could be in fact in the hundreds. Well, that itself is not really a problem yet, but we should take into account that we have our polynomial. That means that we are going to have higher order terms as well, and we even are going to have interactions. And that means that in practice, it is typically not the case that we have only a couple of hundred of different zi's, or we are going to have only a couple of hundreds of, say, elements in our polynomial, but typically we're going to have included, say, a couple of thousand of elements into our polynomial. It could be even a couple of 10,000s of, say, elements that are going to be included in our polynomial. And that could be problematic. That could be problematic because of the fact that in some cases it could even be possible that the number of elements that we're going to have included in pzi is going to be larger than the number of observations that we have. And then ordinary squares is even not going to work. So the question arises, what are we going to do in this particular case? Well, what we have to do first of all is that we have to make an assumption. And the assumption that I'm going to make is the assumption of sparsity. What does sparsity mean? Well, sparsity means that there are going to be only relatively few elements in gamma that are not going to be equal to 0. So what we are going to assume with respect to, say, the regression equation that we have over here is that we have many elements, of course, but most of the elements that we have in pzi are going to have coefficients which are exactly equal to 0. Well, that would be nice, of course, because of the fact that if we would have known the elements that are going to be, that are going to have coefficients that are equal to 0, then we can just take them out. And because of the fact that that's the majority, that would actually solve our problem. Then we only are going to include those elements for which we do know that the gammas, the corresponding gammas, are not equal to 0. But the problem, of course, is that we do not know these elements. We do not know which elements of pzi are going to have coefficients which are equal to 0, and which one actually do not have elements or coefficients that are equal to 0. But now we should realize that we do actually have a very nice method that can help us here. And that is lasso. Lasso is, of course, a very nice method, and the reason behind that is because of the fact that we should realize that lasso is actually able. What does lasso generally do? At the moment that we have a pzi that is of a very high dimension, then we do know that, depending of course on the level of lambda, that most of the coefficients, they will actually be set equal to 0. And that is quite nice because of the fact that then at that moment in time, we probably already know the, say, coefficients that are going to be equal to 0. That is a potential that we have with respect to lasso. Well, we should take into account that we should be a little bit careful here. The first thing that we should realize that at the moment that we're going to do a simple lasso, then it could be possible that even the beta coefficient is going to be set equal to 0. So it might even be possible that the I is going to be essentially kicked out by lasso. Well, that's not what we want in this case, because of the fact that that implies, of course, that we are not able to estimate then our average treatment effect. So therefore, in order to admit that, what we typically do is that we then are not going to give a penalty term to the beta coefficient. That implies that when we are for sure that the beta coefficient will not be set equal to 0 by lasso. That's the first thing that we actually could do in this particular case. So that's the and that's actually how we could do it in this case. We could then simply say we're going to run a lasso regression, and then we are simply going to look at those, say, gammas which are going to be set equal to 0, and hopefully we will only have a very small set of, let's say, gammas that will not be equal to 0. And then what we could do is to simply then use beta as an estimator for the average treatment effect. Well, this is still not such a great idea, and the reason behind that is because of the fact that, well, the beta coefficient will generally not be, it will also be squeezed usually, and also the gamma coefficients will be squeezed. And therefore, what we usually do in this particular situations is that we are not going to look at standard lasso, but we're going to use post lasso. What is post lasso different from standard lasso? Well, in post lasso, what you actually do is that you first are going to look at those, say, coefficients which are not equal to 0. And then in a second stage regression, you're going to include only those elements for which the gamma coefficients were not equal to 0 in an ordinary squares regression. That is what post lasso actually is. Well, this sounds like a very great idea, but unfortunately, it actually doesn't work. And the problem why this actually doesn't work has to do with the fact that what does lasso usually do? Well, what lasso actually does is that it's a very, I would say, intelligent method in order to see essentially which elements that we're going to have are going to give us additional information to get a good prediction. But that is also problematic in this particular case. And the reason behind that is because of the fact that it could be possible that some of the elements that we have in PZI could be highly correlated with the DI that we have. Why is that problematic? Well, that could be problematic because of the fact that then what lasso actually does is that if a particular element of PZI is highly correlated with DI, well, then what we typically are going to do is that it's going to be taken out from the lasso regression. The gamma coefficient is going to be set equal to 0. And the reason behind that is because of the fact that it doesn't add that much of information. Because what does correlation mean? Well, correlation essentially means that actually the information that is already captured in DI is also captured in PZI. And because of the fact that we cannot actually take out DI, that means that it's going to be very likely that in this particular situation, the element in PZI that is going to be highly correlated with DI is going to be kicked out of the lasso regression. And that will be even the case at the moment that the corresponding gamma coefficient itself could be high. So even in the case that the gamma coefficient is going to be high of that particular element, it could still be the case that actually lasso is going to kick it out whenever there is a high correlation between PZI and DI. But you should realize that if from, say, a lasso point of view, from a predictive point of view, this might be a very great idea because of the fact that this particular element doesn't add that much of information. But from an econometrics point of view, there's a really big problem. And the reason behind that is because of the fact that PZI, the element of PZI, is highly correlated with DI. In addition to that, we do know that PZI itself has an impact on YI because of the fact that the gamma coefficient is far from 0. And that implies, of course, that what we have in this case, if we do not include it, is that we are going to have a problem that is well known as being an omitted variable problem. And that means, of course, that the coefficient that we're going to estimate, including, of course, the beta coefficient, is going to be inconsistent. And that is, of course, a problem. The question now arises, how are we going to solve this? Well, in order to solve this, the best thing to do is that we are going to make the correlation between zi and di, so the correlation between the pzi and the di, we are going to make it essentially explicit. How are we going to be able to do that? Well, then what we're going to do is that we're simply going to write down another regression problem. Then we are going to have di at the left hand side, and we're going to have mzi plus vi at the right hand side, where m now is going to be another unknown function of, say, zi that's going to have an impact, in fact, on the di. In addition to that, we are going to assume here that vi is again going to be uncorrelated to our zi. Well, what we can do then in that particular respect is that we can then actually write it another time in an approximation format. Then what we're going to have is di at the left hand side, and on the right hand side we're going to have delta plus pzi, take into account that I now actually have exactly the same polynomial that we had before, but because of the fact that this is a very, I would say, flexible polynomial, we can use it, of course, for yi, but we can also use it for di. So we're going to have pzi now multiplied by zeta, and then in addition to that we are also going to have, say, our additional terms. First of all, the approximation error, that is now denoted by r2i, and we're going to have our error that we already had at the previous slide, our vi. Now what we can do is that we can substitute this, say, regression equation into the regression equation that we already had. Remember that we already had this regression equation, yi is equal to alpha plus di beta plus pzi gamma plus r1i plus ui. And what I can now do is to include, in fact, or substitute in the regression equation that we have here on the first line. If you're going to do that, then what we're going to get is this specification that we have over here. Well, then the next thing that I can do is that I can get rid of the parentheses. That implies, of course, that I get delta multiplied by beta. I get pzi zeta multiplied by beta, and also r2i and vi, they're going to be multiplied by beta. This finally gives me this relatively simple regression equation. And it's simple because of the fact that we do see that we have a constant which is now equal to alpha plus delta times beta. And in addition to that, we are going to have, say, a pzi, our, say, polynomial that we already had, but now multiplied by gamma plus zeta times beta. And we have a bunch of additional terms that actually are uncorrelated with the zeta I that we have, or the zi that we have. So we should realize that this actually can now also be estimated. And this suggests the following strategy. What we could do now is to run, first of all, a lot lesser regression of yi on pzi, take into account that because of the fact that we substituted in di, we don't have di anymore. And then what we could realize is that then in a second stage regression, in a second stage ordinary squares regression, so again we are going to have here post lasso, in fact, in a second stage regression we are going to regress yi on di, but also on the, say, in stage 1 selected regresses. And then the coefficient of di, our beta, is then going to be our average treatment effect. And take into account that at the moment that we're going to do that, in our, say, first stage lesser regression, we are going to immediately see that, well, one of the reasons why particular pzi's or elements of pzi are going to have coefficients away from 0 is not only because of their gamma, but also because of their zeta. And we now see that actually this implies that, in fact, well, say, variables that are highly correlated with di are now going to be included as well, unlike what we had before. This sounds like a very great idea, but unfortunately we should realize that this still doesn't work. And this still doesn't work, well, that is actually quite technical, but it is described by Bologna et al. In 2014 in a paper in Review of Economic Studies. They actually showed that this estimator is still not square root n consistent. That means that there is no convergence of normality of the square root of n multiplied by beta hat minus the average treatment effect. And that is, of course, still a serious problem. Therefore, what they do is that they come up with an alternative. What I say is that what we should do is that we should aim for a three-stage procedure. First of all, we run a lasso regression of yi and pzi. Then we run a lasso regression of di on pzi, so two lasso regressions, one where yi is the left-hand side variable, and one where di is the left-hand side variable. And then finally we're going to run a, say, post-lasso, an ordinary least squares regression of yi on di plus the union of the in stage 1 and 2 selected regresses. I would like to go on with the second method that I wanted to discuss in this particular video, and that is the method of synthetic control groups. In order to introduce synthetic control groups, suppose that we have the standard difference in differences framework. Well, I suppose that you have heard about difference in differences before from other courses. In the case that you have never heard about difference in differences before, well then do not worry. I'm going to discuss this shortly. In addition to that, we should realize that difference in differences is only a byproduct of synthetic control groups. However, what we are going to have is a situation in which we have two time periods. Usually we are going to have one period before a particular treatment and one period after a treatment. And in addition to that, we have a set of observed units, and we're going to denote them by YIS, where S is only going to have 0 and 1. It's the time indicator. So that means that the first period is going to be period 0 and the second period is period 1. And in addition to that, we are also going to have a situation in which we have our I, and I is going to run from 1 till k. So that means that we have in total k units. Now we should realize that, and that is quite different from difference in differences, in synthetic control groups, it is the case that the number of observations that we're going to have per unit in a particular time period could actually be quite small. That is not the case in difference in differences, because of the fact that there you usually assume that even within a time period, well, a particular unit will actually have many different observations. But that's not usually the case with respect to synthetic control groups. We're even going to see a particular example in which we only have one observation per, say, time period for one particular unit. And in that sense, it's best to think in this case that the observed units are going to be averages of individual observations in a particular unit. And then we can look at our example. Abadi, in a paper in 2015, they actually consider the average number of cigarette packages smoked in different states in the US from 1970 to 2000. And now we are mainly interested, or they were mainly interested in one particular state, and that was California. California introduced a 35 cents tax on a package of cigarettes in 1989. In order to give you some idea of how large this increase was, the original taxes were only 10 cents, so it was increased by 25 cents. Nowadays, of course, 35 cents should be considered as really low, because of the fact that even though I've never been in California, I never have been buying any kind of package of cigarettes, I'm pretty sure that, say, nowadays, the taxes are much higher than 35 cents on a package of cigarettes. And the reason why I do think that that's true is because of the fact that if you're going to look at most countries, including actually the Netherlands, well, the, say, taxes on cigarettes has been increasing quite a lot in the last, say, couple of decades. And I'm pretty sure that now in the Netherlands, say, it is much more than 35 cents that you have to pay for a package of cigarettes. But we should take into account that essentially, well, by that time, having a tax of 35 cents was actually enormous. It was high in California, of course, by that time, but we should take into account as well that it was high in comparison to the other states at that time, which usually did not have that high taxes at that moment in time. In addition to that, California used 5 cents in order to prevent the youth from starting to smoke. So it was really, well, this, say, taxes were really introduced in order to prevent people to start smoking. Well, in order to see how this actually works, what we have here is a picture where we have on the x-axis the years. So we actually have it from 1970 up till 2000. And on the y-axis we have the number of packs smoked per year. And first of all, let's look at California. Of course, we have here the year 1989. Actually, I've done it here. The line that we have over here is at 1988 because of the fact that we have yearly data, and that means that what I'm going to do is that I'm going to look at the last year in which still, of course, we had the low taxes. And then at the moment that we're going to look more in particular to the cigarette consumption in California, then we do see that in the year 1970, there were, the number of packs being consumed by every individual in California was around 120. Take into account that that's actually quite high because of the fact that that of course means that, that is about 1/3 of a package per day. Now for smokers that is maybe not that much, but even in 1970 you should realize that there were quite a lot of people that did not smoke, and that implies of course that, this is among the, say, total population. So therefore I would say that 120 is actually quite high. However, we do see that in the years from 1970 to 1975, it still increased a bit. It's increased to almost 130, but then from 1975, 1976, we do see quite a big decrease with respect to cigarettes consumption. We do see that it actually decreased. It also decreased in the period, of course, of 1988, 1989, but it even decreased even further. And we do see that cigarettes consumption, or the number of packages being bought by the average, say, Californian person, was a little higher than 40 in 2000. Question, of course, arises, how does that work out for today? Well, if you're looking at the most recent figures, then there has been even a further drop with respect to cigarette consumption. People in California nowadays don't smoke that much anymore. It's only 11 packages per year per, say, Californian citizen. So that is actually not that much, and you could actually say that that's about, even less than 10% as it was the level of 1970. But the question, of course, arises, how does this compare to the other states in the United States? Well, what I've done is that I have here done a unweighted average of the other states. So this is just all the other states that we have, and we should take into account that these are of course some of the bigger states like New York, but we also have included very small states over here. But if you're going to look at that in the red curve that we have over here, then we do see that in 1970 roughly cigarette consumption in the other states was roughly the same as in California, but we do see that the increase in the 1970s was even sharper than in California, and we do see that it even increased to about 140 packages per year. But also there we do see that there has been a decrease. However, the decrease has been somewhat less than at the moment that we're going to look at California, and we do see that then at the moment that, for example, we're going to look at the year 2000, there's quite a big difference between, I would say, cigarette consumption in California and that in the rest of the United States. What we would like to do now is that we would like now to look at the impact of this particular treatment. So the treatment that we have in this case in 1988, 1989, or going from 88 to 89 with respect to cigarette consumption. What we are going to do is that we here are going to assume that unit 1 is going to be the treated unit. So that means in our case that 1 means California. And we are going to also assume that the second period is going to be the treatment period, and that means that in the first period there's no treatment at all. and we are interested in estimating the average treatment effect among the treated. Well, the average treatment effect among the treated is almost identical to the average treatment effect. It is equal to the mean difference of y1 and y0, but now only for the subset or the subgroup of individuals that are actually treated. So for that subgroup for which di is equal to 1. So the average treatment effect among the treated is equal to the mean of y1 conditional on di equal to 1 minus the mean of y0 conditional on di equal to 1 again. So that's the average treatment effect. Take into account that like what we had with respect to the average treatment effect itself, the average treatment effect among the treated, what we do have is that the first part of the average treatment effect among the treated, actually that part is always identified because of the fact that it is exactly equal to the mean outcome among those individuals who are treated. But the second one is much more difficult because of the fact that the second part, of course, with respect to the second part, well, we have to look at a, say, counterfactual outcome of, say, the treated in the case that they would not be treated. Well, there are a couple of difficulties, of course, with respect to identification, but let's not consider that at this moment in time. But what we could do is to try at least to estimate it. And we could, of course, try to estimate this by simply looking at, say, the observed values of the treated unit that we have. We have observed values, I would say, before the treatment, and we have observed values after treatment, and we could compare them with each other. So one potential estimator of the average treatment effect among the treated is simply equal to, say, the observation in the second period, in period number 1, for the first unit, minus the observation that we had in period number 0 for that same unit. So then we get y11 minus y10. But we should take into account that there is a problem with respect to this approach because of the fact that this approach actually assumes that there is no trend over time with respect to the outcome variable. And that's definitely not true. At the moment that we are going to look at, for example, at California in our case, then one thing that we could, of course, do is to compare 1988, which is at the dashed line, with the year after 1989. And then we do see that there is quite a big difference, of course, in terms of cigarette consumption. And that implies that we could actually say, like, well, cigarette consumption has decreased because of the introduction of this additional tax. However, at the moment that we're going to look at the whole picture, then we actually do see that cigarette consumption also decreased in many other years. Actually, it has been decreasing ever since the year 1975-1976. So therefore, it is quite strange then to assume that cigarette consumption would even have stayed the same at the moment that we would not have introduced, say, our increase with respect to taxes. That's even more clear at the moment that we even are going to look at the other states. Even for the other states, we do see that there is a decrease with respect to cigarette consumption in the years 1988 and 1989, comparing these 2 years with each other. But we should take into account that, of course, for the other states, the fact that, say, the taxes in California actually increased, well, that doesn't matter, of course. You are not going to smoke less because of the fact that in, for example, New York, because of the fact that in California, the taxes have been increasing. So you should realize that, well, we immediately see that there is actually a trend, and that actually can make the, say, this estimator that we have over here, the before-after estimator, well, that estimator definitely is not going to be the correct kind of estimator. In that sense, it would be better to compare the outcome in period 1 of the treated group with the counterfactual outcome that would have taken place in period 1 when treatment would not have occurred. Well, we will later on ask ourselves the question how we are actually going to get that, but what we're going to do is that we first of all are going to denote this outcome by y11c. So c in this case is for counterfactual, and that means that very generally what we can say is that our estimator of the average treatment effect among the treated is now going to be simply equal to y11 minus y11c. We should of course take into account that the problem is that y11c is actually not observed. So we can not actually directly observe this y11c. So in order to get this estimator of average treatment effect among the treated, we have to make some kind of assumptions. Well, now we should realize that difference in differences actually makes an assumption with respect to that. And the assumption that is usually made with respect to the difference in differences is that, well, what it actually does is that it says y11c, first of all, equal to y10. Well, that is of course the situation that we already had before in this with respect to this estimator. What we simply say is that the outcome that we would have had in the case that we would not have any treatment for the treatment group would have been just the outcome in the period before, so y10. But in addition to that, we are going to add a trend to that. And what we essentially are going to do is that we're going to use a trend from, say, the other, say, states. So what we're going to do essentially is that we're going to simply take the, say, difference that we have over time with respect to any of the other control units. So that could be New York, it could be any other kind of state. And that means that we're going to add to this yi1 minus yi0, which is essentially nothing else as the difference that we're going to have with respect to the other states. So in words, the control unit I is assumed to have the same trend as a treatment unit 1 if treatment would not have occurred. Well, it's very difficult to check that, of course, because of the fact that we should realize that this is this common trends assumption that we have over here. Well, it can actually not be checked because of the fact that since we do not know what y11c would be, we can also not check whether this common trends assumption is going to be correct. As an alternative, Alberto Abadie, in a couple of different papers, he introduces so-called synthetic control groups. That is in a paper by already a long time ago in 2003 by Abadie and Kadisibal, but also by Abadie et al. In 2010 and 2015. A so-called synthetic control group is actually nothing else as a weighted average over the control group. So that implies that our y11c, our, say, counterfactual observation that we would like to look at is going to be equal to essentially nothing else as a weighted sum over the outcomes of the control units. So that is the sum that runs from 2 till k, the number of control units that we actually have. Well, for some set of weights omega I that we have. Well, usually what we're going to do is that we're going to assume that the weights should be at least as large as 0. In addition to that, we are going to assume that the sum over the weights must be equal to 1. This is one of the restrictions that we're going to have with respect to the weights. But other than that, what we are going to do is that we essentially have to ask ourselves the question, what are the weights that we are going to do? Well, one of the things that we could do is that we could just simply take one particular state in our analysis, and for that state we are going to use a weight equal to 1, and for the other ones we are going to have a, say, weight equal to 0. Another thing that we could have done is that we could have given all the states exactly the same weight. Then we would have been back in this picture that we have over here. That essentially implies that what we're going to do is that we are going to try to essentially predict the, say, outcomes that we have with respect to California in 1989. We're going to predict them by, in fact, the outcomes, the average outcome that we have in the other states. And that implies that at the moment that we're going to compare the red curve with the blue curve that we have in 1989, so just after the dashed line that we have, then we're going to see a big difference between the red and the blue curve. And that implies that since the red curve is much higher than the blue curve, that actually implies that we then would expect that the increase with respect to the taxes has decreased, say, smoking consumption, cigarette consumption by quite a lot. But you might say that in this case, that would be the wrong conclusion, at least based on what we are going to look at right now. And the reason behind that is because of the fact that we should realize that there's not only a difference between cigarette consumption of the other states and California on the average of the other states, so the red curve that we have over here with California in 1989, but we also see it in, for example, 1988, and also in all of the other years that we have in our analysis, apart of course from 1970. So therefore we should realize that that might not be such a great choice. Maybe a better choice is to make at least the, say, outcome for 1988 exactly the same for California and essentially our synthetic control group. And that implies that we're going to use the weights in such a way that we are going to have that the red line that we have over here is going to be exactly equal to the blue line, at least in 1988. What does that mean? Well, that essentially means that we are going to set our weights in our case in such a way for, say, the control states, so the states yi0, where I runs from 2 till k, we're going to set the weights in such a way that they're exactly equal to the outcome of the treatment state, the treatment unit, in the very first period, period 0. So that means that we are going to make y10 equal to, in fact, the sum over the weighted average. Of course, y10 is something that is given to us, and of course the right hand side we can observe as well, but we're going to, well, set the weights in such a way that the left and the right hand side in this equation, they are going to be equal to each other. Now you should realize that this actually potentially has multiple solutions. It's actually not that difficult given the fact that we have only one particular restriction and we have many unknowns, essentially all the states that we have in the United States apart from, of course, California. That implies that we have many unknowns with respect to the omegas. So it is not that difficult to find the combination of the omegas for which this equality is going to be true. But it's most likely that we are going to do that for different kind of weights. And that is of course not so great. So therefore what we could do is that we could also use the other periods. When there are many pre-treatment periods, then we can actually make the pre-trends equal to each other. That brings us to a somewhat richer model. Suppose now that there are t periods and that the treatment takes place in period t0, where t0 is now going to be smaller than t. So that means that they are not just going to have just 2 periods in time, but we are going to have t periods in time, where t of course could be much larger than 2. We're still going to denote the observations by YIS for unit I and period S, and unit 1 is still going to be the treated unit and the others are going to be the control units. That means that in our Californian smoking example, one could of course use the period between 1970 and 2000, which implies that t then is going to be equal to 31, t0 is going to be equal to 19, and k is going to be equal to 38. It implies that we are not going to use all our states in the United States. That implies that then what we're going to do is that we now are going to be able to predict our counterfactual outcomes for the treated unit. So now what we're going to have is y1sc, where s can actually run from t0 plus 1 up till t, and we're going to predict them as a weighted average over the observations that we have from our control unit. So we're going to have now again a weighted sum over the observations where the weights are again equal to omega I. Then the question arises, how are we then going to set those weights? Well, we are going to set those weights in such a way that the pre-treatment outcomes between our, say, observed treatment unit is going to be exactly equal to the control units with respect to the weighted averages that we're going to have. So we're going to set now the weights in such a way in the periods before treatment, so that means that S is in between 1 and T0, we're going to set the weights in such a way that they're going to be exactly equal to the outcomes Y1S in the period before. So the treated units, the outcome of the treated units must be equal to the weighted average of, in a sense, the control units. So we are going to set the weights in such a way that this equality is going to hold for, say, all the periods that we have before treatment. So the periods from 1 till T0. Now the problem that might arise that at the moment that we're going to have many periods in the pre-treatment period, so we're going to have that T0 is going to be really, really large, then it might be possible that it's going to be impossible to find an omega I, a set of omega i's, for which this also always is going to be true. Well, in that particular situation, what we could do is that we could then minimize the following minimization problem. So instead of setting the Y1S in such a way, or in fact the weights in such a way that Y1S becomes exactly equal to the weighted sum, what we're going to do is that we're going to set the weights in such a way that the difference between the two is going to be as small as possible. In words, this implies that we try to mimic the pre-treatment outcomes as close as possible between the control and the treatment group. How is this going to look like in our case? Well, in our case, we still have the year on the x-axis and we still have the number of packages per years on the, say, y-axis. And then what we're going to get is that we are going to have, first of all, in the period between 1970 and 1988, so the blue line, the vertical line that we have, is actually nothing else as a line at 1988, the last period that we have before treatment. And we're going to see that essentially we have set the omegas in such a way that we do see that the red and the blue curve, they are as close as possible to each other. But then after 1989, or starting in 1989, we do actually see that we are going to now make our predictions. So it implies that the blue curve is still based on our observations from the treated unit, from California of course, but the red curve now is based on essentially making our predictions, the predictions that we have over here, in order to, well, use the weights and make our predictions based on the control states. Using, of course, the weights that we have determined in the period before the treatment. And now what we see is that because of the fact that the red curve is well above the blue curve, that means, of course, that we have a negative impact. The average treatment effect, in this case, the average treatment effect among the treated, is negative, which makes sense, of course, because of the fact that we may expect that at the moment that the taxes are going to increase, that then the cigarette consumption is going to be decreasing. And we do see that there is quite a big difference between the treatment and the control group, and that in our case is our average treatment effect among the treated.